Hello, everyone. Thanks for coming today. My name is Dimitris Mouris, and I will present to you our latest work called Pick Your Frequency, Advanced Search of 3D CAD Files in the Fourier domain. In this work, we developed a new methodology to enable search for 3D CAD files using exact and partial shape characteristics. First of all, I would like to acknowledge my co-authors in this work, Gouert and Nektarios Tsoutsos from the University of Delaware, and Nikhil Gupta from New York University. I would also like to acknowledge NSF for supporting this work. The 3D printing market has grown to $10 billion US in 2019, and it's expected to grow to $16 billion in 2020. The main reason for this is that 3D printing enables developing and testing 3D parts digitally, and also has various applications in different industries. For example, in aerospace, where we have parts of jet engines that are 3D printed, or in automotive, or even in medical, where we have implants and advanced prosthetics. As you all know, we have different search engines that enables us to search based on a keyword or even a sentence. We have the ability to search in our own emails using a keyword or filter them out based on a center. However, we do not have the ability to search in 3D printing. Although we could always use a keyword to find a 3D object, we cannot use a 3D object itself to find similar objects. So in order to understand how important that is, I want you to imagine a world where we do not have the ability to search in our own emails, or search engines do not exist and we're just exposed to the internet. In this work, we developed a new methodology that enables us searching using 3D objects, and we can get back both exact and partial shapes matches. But first of all, how do we encode 3D objects? CAD file formats exist in both proprietary and open source. For example, a Parasol file format is proprietary, while STL and STEP file formats are open source. In this work, we focus on STL files that represent surfaces as triangles, and due to that, they have varying granularities. For example, if we design a sphere in a CAD software tool and export it as an STL file, we will end up with either of these three representations, where figure B has significantly higher resolution than figure D because it comprises more triangles. As I already mentioned, this work focuses on STL files, and the main reason for this is that STL files, every other different CAD file format can be easily translated to STL files. Before we dive into our methodology, I would also like to talk about traditional audio recognition. In audio recognition, we use Fourier transformation to generate a spectrogram from an audio sample, and then extract the points that have the highest amplitudes. We call them the peaks. And for each two of the peaks, we generate a hash digest. We continue this with all the remaining peaks, and the set of the hash digests uniquely identify the audio sample that we started with. In this work, we developed a new methodology to enable exact and partial search for 3D models. For instance, if we search for a screw in a database that contains this screw and other screws as well, exact matching means that we will get back the exact same screw, while partial matching means that we will get back similar screws as well. To instantiate our observation and our methodology, we created the Fourier fingerprint search framework that starts with a 3D CAD file and generates a digital identifier of that file, which we call a fingerprint. The fingerprint essentially is a set of hashes that uniquely identifies this 3D CAD file. Finally, we enroll all the generated hashes, the fingerprint, in the database. To sum up our contributions, we generate the framework to enable search using 3D models. Our framework is flexible since it can be tweakable depending on the shape we're searching for. And also we have developed 4 advanced feature techniques that significantly improve our searching accuracy. Now, I want to delve into more details about the individual steps of our framework. Starting with an STL file, we logically divide it into a configurable number of slices, and we repeat this process for all axes. Then we project these 3D slices onto each of these 3D slices onto a 2-dimensional grid, and we apply the two-dimensional fast Fourier transformation to get the frequency representation. We find the points that have the highest magnitudes in this frequency representation, and we filter out the rest of them using a filter. Then, starting with the first peak, which we call an anchor, we generate some, we pair this anchor with the next peaks and compute some signatures. A signature is a unique encoding that carries information about the frequencies of the anchor and the next peak, as well as the magnitudes and the slice, which slice this anchor and the peak came from. Next, we use the next peak as an anchor and generate some more signatures. Finally, we enroll all the signatures in the database. Now that we have a way to generate some fingerprints for different files, we want a way to rank the similarity between these fingerprints. So we came up with two strategies. The first one is called matching neighborhoods and is motivated by pattern matching techniques. For this strategy, we introduced the concept of a neighborhood, which are all the signatures that have the same anchor point. For example, these five signatures comprise one neighborhood, while these four signatures comprise another one. In order two neighborhoods to be considered a match, we want to share at least a number of signatures. And of course, we rank higher the file that shares as many neighborhoods as possible with a query file. Our second strategy is called fine-grained matching and prioritizes individual shape characteristics over bigger but more difficult to match patterns. In this strategy, we try to match as many individual signatures as possible between the query and the search file. For example, each one of these arrows represent one signature. Furthermore, we introduce 4 advanced matching techniques to improve the accuracy of our framework. The first one is called rotation of slices, and the idea is that if our query is a slightly modified version of an object that we have in the database, we want to increase the probability of finding this model. To do that, when we enroll a file in the database, we also enroll multiple rotations of this file across all 3 different axes. So when a query comes and the query is either transformed or rotated, by having stored all these rotations, we have better chances of finding it in the database. Our second matching technique is called star rotation, and it's motivated by 3D object scanners. The 3D object scanners slowly rotate an object and take multiple pictures of it in order to create a digital identifier of this object. So in this technique, we rotate an object and slice it across the rotational axis and generate some more signatures. Using the star rotation technique, we end up with a more complete representation of this object. The difference between these two techniques is that in the first one, the axis of rotation is perpendicular to the projection, while in the second one, the axis of rotation is parallel to the projection. If you recall from earlier, some STL files may have low resolution. So we came up with a technique which we call interpolation to recursively enhance the resolution of such STL files. We start with a big triangle, the black one in the figure, and we find its center and recursively generate more and more triangles. This technique upscales the resolution of such STL files. In our final technique, if you remember from the second step of our framework, where we project the 3-dimensional slices onto 2D grids, by using this projection, we end up losing some information because we project the 3 dimensions onto 2 dimensions. So in this last technique, instead of doing that, we apply the 3-dimensional fast Fourier transformation directly on the 3D slices. This technique ends up with a better representation of the object. Now I want to quickly move to our experiments. We use an AWS instance and an open source data set that has about 3,000 unique manufacturing models. In our implementation, we used Python 3 and the fast key value storage designed by Google, which is called LevelDB. And first of all, we measured the exact matching capabilities of our framework. To do that, we enrolled all 3,000 models in the database, and we queried it for each one of these models. Then we checked that the correct answer was in the top 3 reported results, which means that we measured the top 3 accuracy. We repeated this process for both 2 and 6 number of slices, and with both of these techniques, the average time was about 1 second. If you see at this, if you focus at this table here, the accuracy for all classes was 100%, except these 2 classes. And the reason for that is that these 2 classes share very similar objects. However, even under these circumstances, using the fine-grained approach and 6 number of slices, our accuracy was almost 100%. Next, we assessed the partial matching capabilities of our framework. Once again, we enrolled all 3,000 different files in the database, and we slightly permuted the STL triangles of the query file, and we also rotated the query file across all 3 different axes. Our accuracy was up to 91% without using any optimizations. And when we used the star rotation technique, our accuracy increased to 100%. We have included a lot more experience in the paper. To sum up, we have designed an efficient and highly configurable framework for searching 3D CAD models. Our framework utilizes multidimensional FFTs to generate unique identifiers that encode the important characteristics of the 3D objects. Our experimental results show that our exact matching accuracy is almost 100%, while our partial matching accuracy, when we start with 80 to 83% accuracy, using the advanced matching techniques such as the star rotations, it increases to 100%. Now, I want to quickly move to a demo in which I have already enrolled all the files from the FabWave dataset in the database, and then we will search for a bolt and a bearing. So I'm using a bearing. Let's let this finish. This is my query file. And as you see here, the first reported result is the same file. And then we have 4 more results that are all from the bearing class. And if we see them, this was the 5th match. The 4th. The 3rd, the 2nd. And our query file, and also our first result. If you see all of them, they look very similar. However, some of them are thicker or not as tall as the others, but all of them look very similar. And the important thing is that the first result is also our query. Now I will search for a bolt. Again, if you see here, this was our query file. The first reported result is also the query file. Then we have another bolt. Then we have 2 socket screws that are not bolts, but look very similar to bolts. And then we have the 5th result is also a bolt. So let's inspect these files.
Dimitris, are these using the 3D FFT or the slicing method?
So here we use the 2-dimensional FFT, and we use 2 number of slices here. Okay. So we use 2 slices and the 2-dimensional FFT using the fine-grained approach. This was our query file and also our first result. Then we got another bolt. The second one is a bolt. Then we got two hex head screws that are not from the same class, but look very similar to bolts. And then we got a thicker bolt. I'd be happy to answer any questions. Thank you for your time. And here's a link to our paper, and our code is open source on GitHub.
Thank you, Dimitri.